Point of discussion is molecular orbital theory, which is very much essential to get basic concepts in chemistry. Now, molecular orbital theory starts with the concept that after the overlap, the atomic orbitals are completely annihilated and forms a new set of orbitals called the molecular orbital. And as example, sigma, sigma star, pi, pi star, delta, delta star, and so on. The more orbital mixing occurs between the similar energy level, and they should be close together and should be in the proper angle. Now see here, these two orbitals, s orbital, spherically symmetric, are getting overlap, giving a sigma bond. And then we have next one, sigma, another sigma one, but that is with one s orbital and one p orbital. So if I take one s orbital and one p orbital, then you will find this type of orbital. See here the difference. In case of this s overlap, we are getting a elongated sort of not perfectly spherical but elongated spheroid. But here the structure is entirely different. This is overlap between s and p orbital, and you are getting this sort of shape. Third one at the bottommost, two p orbitals are getting overlap to give you another sigma bond. So all the three are sigma actually. So first one at the topmost, that is ss overlap. Here it is sp overlap, and now the last of all it is pp overlap. All are giving sigma bonds. Now we are talking about anti-bonding orbital. So bonding and anti-bonding, what is the basic difference? Bonding means there the orbitals are getting overlap in a positive fashion. It is called constructive interference. So, and at the same time, whenever the addition will occur, similarly the subtraction may also occur, and we get anti-bonding orbital. Okay, so this bonding and anti-bonding, these two orbital set we get that way. Two s orbitals are overlapping, give you two sorts of interaction. Then one is addition, that is leads to bonding, whereas another one is subtraction leading to anti-bonding, and we call it sigma and sigma star. Now see, in the right hand side we can take the example, two hydrogen atom. So here one hydrogen atom and here is another hydrogen atom getting overlap, giving you one sigma, and this is called in phase overlap, and whereas this one is out of phase. The in phase overlap is giving us bonding, which is energetically lower, and sigma star, which is anti-bonding, energetically much higher. So this bonding interaction and anti-bonding interaction apparently looking same, but practically the anti-bonding interaction is a bit higher compared to bonding interaction. Now the next example you can take different type of homonuclear diatomic orbital molecules we are forming, like nitrogen overlap, then oxygen overlap. They are all giving homonuclear diatomics, and we get the this is looking like this. Okay, so if we have this one, this bonding and anti-bonding interaction, both you can find here. 2s and 2s overlap, giving us sigma sigma star, and well, here we have given sigma 2s star because this sigma and sigma star, these are inner electronic cores, so interaction is comparatively less. Now you have 2p and 2p overlap, giving us sigma, pi, pi star, and sigma star. Now depending on the number of electron available, they will be getting filled up, and obviously lower energy orbitals will be filled up first, followed by the higher energy orbitals. Next, so we are getting homonuclear diatomics B2, C2, N2, O2, F2. So B2, 2 atoms of boron forming a molecule. C2, 2 carbon atoms forming a molecule. Now the number of electrons for boron is 5, for carbon it is 6, for nitrogen 7, oxygen 8, and fluorine will have 9. Now if I take B2, that means 2 boron atom, one atom is having 5 number of electrons, so total we have 10 electrons for B2. But 1s and 1s star, sigma 1s, sigma 1s star, as they are inner electronic core, so their bonding anti-bonding interaction is negligibly small, so you can ignore them. So now the bonding that I am showing here is only sigma 2s, sigma 2s star, and pi 2p. Others are empty because total we have here out of 10 electrons, 4 we have ignored, so total 6 electrons now you have. 2 are in the sigma 2s orbital, 2 are in the sigma 2s star orbital, and 2 are at the pi orbital. So total we can find 6 electrons here, and 4 are there in the inner electronic cores, sigma 1s star, sigma 1s and sigma 1s star. Now carbon atomic number is 6, so total we have 12 electrons. 4 electrons are there in the inner electronic core, and rest 8 electrons you can find here. Now next is nitrogen, total 14 electrons. So 4 electrons in the inner electronic core, and other electrons are over here. We can find total 10 electrons we can count. Now similarly for oxygen, we have 2 more electrons, so total 16 electrons, 8 electron each atom, so total 16 electrons. Now 4 electrons are in the inner electronic core, and that's why we can find 12 electrons are there in the bonding orbitals. So bonding and anti-bonding. Here bonding, this one is anti-bonding, this one is bonding, and then again bonding and anti-bonding. That way we can find. Now fluorine, total 9 electrons in each atom and 8 electrons for both the atoms, and here you can find the electrons are in the sigma star, pi star orbitals. Now here all the sigma and pi interaction is cancelling each other, and thereby the only one bonding will be there. For fluorine atom there will be only one bonding. For oxygen there will be a double bond. For nitrogen there will be a triple bond, depending on how many number of bonding electrons and how many number of anti-bonding electrons present. Now the bond order is defined as the number of bonding electron minus number of anti-bonding electron divided by 2. So that's why if we consider here how many bonding, total bonding electron, this sigma and sigma star is cancelled over, so only these pi electrons are present as bonding electron. So 2 pi electrons are present as bonding electron, but anti-bonding is empty, and that's why you have a bond order 1. Now for carbon, bond order will be similarly 2. For nitrogen, bond order 3. For oxygen, again bond order 2, because electron is now getting occupied in the anti-bonding orbital, pi star. And for fluorine, you can find again that more and more anti-bonding is getting filled up, thereby bond order is getting reduced. So for oxygen, bond order is 2, whereas for fluorine the bond order is 1. Highest bond order here is for nitrogen, that is 3. So to continue with the different structures, if you can just look at here the structures, these 2 p orbitals and giving lateral overlap. So that's why you can call it pi, because 2 p orbitals whenever giving lateral overlap we are getting pi and pi star. So these 2 are pi and pi star. But here the upper one, this sigma and sigma star. This is sigma star, this is pi, and this is pi star. In the next slide, there is a relationship or comparison between the valence bond theory and molecular orbital theory. In the valence bond theory, we can consider the s and p orbitals are intact. We can consider the concept of hybridization, sp, sp2, sp3, but we have no concept of sigma star, pi star. So in the valence bond theory, the main basic concept is the orbitals sp, df are intact. Okay, that is and undergoing the linear combination. The atomic orbitals are undergoing linear combination, that is addition and subtraction, giving us molecular orbital which are called sigma sigma star pi pi star. So the main difference between the valence bond theory and the molecular orbital theory is that in the valence bond theory we consider only the SPDF orbitals, but whereas the molecular orbital theory, the combination of sp orbitals are giving us sigma sigma star pi pi star, which are molecular orbital, not atomic orbital. But in the valence bond theory only the atomic orbitals are present, and we are considering the overlap between the atomic orbitals, but there is no complete formation of molecular orbital. That is the basic concept, main difference. Next slide, you can go on. Well, so yes, this particular slide is interesting. See here, this 1s orbital, two such 1s orbital getting overlap, giving in phase overlap, giving us bonding. And whenever we are considering bonding, the electron density in the middle of the two atomic orbitals is increased. See, before the overlap and after the overlap, it is increased or enhanced. Okay. Whereas in the right hand side, we are considering anti-bonding orbital. So anti-bonding overlap means out of phase overlap. So for out of phase, the electron density in the middle after the overlap is actually reduced. So here it is increased or enhanced in the middle, here it is decreased in the middle. So in the anti-bonding probability density is getting reduced, whereas the bonding probability density is increased or enhanced due to overlapping. Now, how do we consider the molecular orbital theory? Bonding molecular orbital theory is considered like this: psi MO, that is molecular orbital, bonding molecular orbital, is giving us a combination of psi A and psi B, that is addition, positive interaction. It is also called constructive interference of these two orbitals, constructive interference of the phase. So in phase overlap is giving us bonding, and here psi MO is equal to psi A plus psi B, where psi A is atomic orbital of one atom and psi B is atomic orbital of another atom. Whereas in the anti-bonding, it is subtraction instead of addition. So it is represented by psi star, and which is equal to psi A minus psi B. So this is anti-bonding molecular orbital. So here it is bonding molecular orbital, whereas here it is anti-bonding molecular orbital. So again, the same molecular orbitals, energy, their orbital diagram, these are all called orbital diagram. So these orbital diagrams we are just showing in a different way. So just to get the idea about the different structures, so how the structures are there. So this is PZ overlap head on, giving us sigma. This is anti-bonding, sigma star. Here it is pi, and this is pi star. Okay, the topmost one here, right hand side, just follow my pointer. So here these two p orbitals are getting overlapped, head on overlap, giving us sigma. This one is also head on overlap, but out of phase overlap, giving us sigma star. Now these two p orbitals are giving lateral overlap, giving us pi, and here it is anti-bonding out of phase overlap, giving us pi star. So sigma sigma star, pi pi star in one PPT. So this is the same thing we can observe in the left hand side also. The diagram or drawing is a bit different, but it is representing the same thing, bonding and anti-bonding. Now, homonuclear diatomic molecules, the linear combination of atomic orbital, the linear combination of atomic orbital, here these two are undergoing bonding and these two are undergoing anti-bonding. So here this one is See, one thing is interesting here to understand the linear combination of atomic orbital of n number of atomic orbital if involved, then we get n number of molecular orbital. That means the same number of molecular orbital. The number of atomic orbitals involved will give the same number of molecular orbitals. Just like here, if I take two hydrogen atom involving one s orbital from each atom, so we are getting one sigma and one sigma star for hydrogen molecule, one sigma at the below and one sigma star at the top. So these two structures. Now for hydrogen, the difference in energy between the sigma and sigma star is 11.4 electron volt and bond length is 109 nanometer. Next one, homonuclear diatomic molecules. These homonuclear diatomic molecules, this diagram that I am showing here is applicable for all the homonuclear diatomics. More or less this particular diagram will be true, but there are two type of diagram you can find, left one and right one. In the left one, the sigma here, sigma 2pz is below, whereas this pi 2px and pi 2py is above. Whereas here in the right hand side one, the sigma is 2p, sigma 2p is above and pi 2p and here is below. These two types of energy diagram is observed. So if I take boron, carbon, nitrogen, we can find the structure that is there in the right hand side, whereas if I take oxygen or fluorine, that means atomic number 8 or atomic number 9, we can find the energy diagram that will follow is the left one. Why it is so? Why is there difference? Because here this sigma 2 sigma star 2s and sigma 2pz, these two are having interaction, and because of these both are sigma, so sigma sigma star interaction is making this one repel or it is going above. But for oxygen, this type of interaction is not happening because this energy difference between the 2s orbital and 2p orbital is higher in case of higher atomic number like oxygen or fluorine. So that interaction is becoming less as the distance is increasing. This distance between the energy level, this 2s orbital and 2p orbital, the energy level is difference is more, so this interaction is becoming reduced. Whereas the right hand side one, here sigma 2s star is interacting with sigma 2p, and so because of this sigma sigma interaction, the sigma 2p is going above pi 2p and x and pi 2p y. Now right hand side you can get the formula for bond order. Bond order equal to half into number of bonding electrons minus number of anti-bonding electrons. Now another interesting thing here, magnetic property. Whenever you are having fully filled electrons in the molecular orbital, if it is totally fulfilled, that means that sigma sigma star, the electrons are paired up, then you can find the magnetic property that it will be diamagnetic in nature, electrons are paired. But if the electrons are unpaired, we get paramagnetic property. And that's why oxygen is found to be paramagnetic. According to molecular orbital, that oxygen is found to be paramagnetic because there are two electrons in the pi star 2px and pi star 2py orbital. So as these electrons are not paired up, so that's why that paramagnetic property is observed. Now in this slide, this next slide, what you can find here, left hand side, this constructive interference, bonding interaction, and right hand side one, the destructive interference, out of phase overlap, or also called anti-bonding interaction. So left hand one is bonding interaction giving a elongated spheroid, and in the right hand side the interaction between the two spherical orbital is giving us a deformed shape like this. So it is anti-bonding interaction is giving this deformed shape, whereas the bonding interaction is giving us this overlap, okay, and it is giving the elongated spheroid structure. Now helium molecule, this is the molecular orbital diagram, sigma sigma star. it is also written here sigma G and sigma star U, because G for Garrett. So the sigma is spherically symmetric, sigma is symmetric, that's why it is Garrett, means even, whereas sigma star is ungarrett, asymmetry. See the symmetry structure and asymmetry here. So this is symmetric structure. So from the center, if you draw a line, both sides you are getting same. So that's why it is symmetric. But here at the center, if you take the position and from there if you draw a line, right hand side and left hand side, so here you are getting blue, but here you are getting red. So they are having different symmetry, and so this is called asymmetric. So that means sigma star is asymmetric and asymmetric is ungarrett. So that's why it is represented as U. So here this sigma is garrett and sigma star is ungarrett. So it is, that's why it is written sigma U, and here it is written sigma G. G for garrett means even, means symmetric, and sigma star is U, means ungarrett or asymmetric. So here the comparison between hydrogen, hydrogen ion, hydrogen helium plus and He2. So what will be the magnetism property? For H2 is diamagnetic, H2 plus is paramagnetic, because there is only one electron in the bonding orbital, that's why it is paramagnetic. He2 plus, again there is a one anti-bonding electron in the pi star sigma star orbital, that's why it is paramagnetic in nature. He2, it is diamagnetic, it is not actually forming, so He2 cannot form because the number of bond order is 0 and number of bonding electron and number of anti-bonding electron is equal, and that's why bond order is 0, and that's why the molecule does not exist. Lithium molecule, here the structure of lithium, one sigma star cancelling each other, one is sigma 1s star, if you consider this is cancelling each other, but you have sigma G and sigma U star here, and this is formed from 2s, so that's why sigma 2s, here it is represented G, and here it is sigma star 2s, and it is printed as U. So this one is garrett, this one is ungarrett. So this is symmetric bonding, this is asymmetric anti-bonding. Now beryllium, the bond order is 0 because number of bonding electron and number of anti-bonding electron totally becoming equal here, so it is cancelling, and so it is not stable. So Be2 does not exist, like He2 does not exist, but Li2 can exist theoretically. Beryllium Be2 does not exist because bond order is 0. Next, go to oxygen here as another example. So this is the electronic configuration of the molecular orbital, sigma 1s star, sigma 2s star. The electrons are getting filled, so they are all cancelling each other, but there are two unpaired electrons existing at the sigma pi orbitals, pi 2px and pi 2py, and both are anti-bonding orbital. There it is pi star, this is also pi star. So one electron residing each in that pi 2px and pi 2py orbital, one electron there, and this is all in the anti-bonding orbital. So what is the bond order? If I consider the bond order, number of bonding and number of anti-bonding, so here number of bonding electron is 6, but here number of anti-bonding electron is 2, so 6 minus 2 by 2, so the bond order, net bond order is becoming 2, and molecule will be O double bond O. Next is O2 plus, O2 minus, this sort of structure. So here one electron removed here, so it is O2 plus. So if I consider O2 plus, the bond order will be 6 minus 1 by 2, that means 5 by 2. Okay, and right hand side the bond order will be 6 minus 0 by 2, that means 3. So O2 2 plus, the bond order will be 3, O2 plus bond order will be 2, because as we are removing electron from the anti-bonding orbital, so bond order is increasing. So this one unpaired electron present, that's why paramagnetic, but right hand side one O2 2 plus, the magnetic property will be diamagnetic because the no unpaired electron present here. As you can see, no unpaired electron can present here, and that's why O2 2 plus, if we consider, it will be diamagnetic, whereas O2 plus, if we take, it will be paramagnetic in nature. Next, one electron extra we are given, so it is O2 minus. If I take O2 minus, then the bond order will be 6 minus 3 by 2, that means 3 by 2, whereas here bond order will be 6 minus 4 by 2, that means bond order will be 1. So this is O2 2 minus, so this is O2 minus, bond order 2 and 1 and half, and here it is O2 2 minus, bond order is 1. And by the way, so this is again paramagnetic because one unpaired electron present. This is diamagnetic because no unpaired electron present here, all are paired electrons. F2 molecule, if you consider the electronic configuration is just like O2 2 minus, total 18 electron, we have 9 each, this side 9, this side 9, total 18 electrons. So bond order will be 6 minus 4 by 2, that is 1. So we know that F2 has a bond order 1, so F dash F, we light the molecule that way. Now neon, total all the electrons are filled, okay. So in the outermost electron field, the outermost level, we can get 16 electron here. So that's why we can find it is like this neon, the electronic configuration total 20 electrons, and totally filled, there is no unpaired electron, that's why the bond order will be 0 and the molecular does not exist, and if it could exist, it should be diamagnetic. This is B2, C2, N2. The position of the orbitals will be like this, left hand side. Now O2, F2, Ne2, the orbital energy diagram, if we draw, will be like this. So here sigma is below, pi is above, but here pi is below, sigma is above. This is B2, this is C2, N2. They are all similar,